Hello, this is Deborah Dunling Chung, D.D.L. Chung, Zhong Duanling. I'm at Buffalo. I'm happy to share with you today carbon fiber multifunctionality. Special thanks to Wuhan University of Technology for hosting my lecture today. Also, special thanks to the State Key Laboratory of Silicate Materials for Architectures under this university. I first visited this university in 2002 and gave a lecture to a large group of students. Wuhan is a very important city in the history of China because it's the Wuhan uprising that led to the overthrowing of the last dynasty of China, thus changing China from an empire to a republic. And that's the Chinese Revolution of 1911. And this museum is still there in Wuhan. My maternal grandfather is here, Mr. Chan, and also his wife, my grandmother, Li Sun Chao. And my grandfather was a revolutionary under Dr. Sun Yat-sen. He belonged to the section of the Chinese Revolutionary Alliance in Guangdong province. He traveled from Hong Kong to Singapore to prepare for the revolution. And in Singapore, he founded a newspaper called China Rise and also started a bookstore. And both newspaper and bookstore were to promote the revolution. And this is the issue of that newspaper in August of 1907. Also, grandfather raised in Singapore over 30,000 yuan for military use in the revolution. My mother, Rebecca, was born in Guangzhou in 1920. That's after the 1911 revolution. And that was when grandfather was serving as a senator in Guangzhou. And this is a 1923 Guangzhou newspaper that mentioned grandfather's work as an elected senator of Guangzhou. Later, grandfather retired in Hong Kong in Qingyi Island. And there he wrote this very touching poem about the revolution. 铁血战残青. My mother, Rebecca, during World War II, joined the Flying Tigers in Kunming, China as a nurse. And this is the clinic of the Flying Tigers with my mother on the left in 1942 to 43. And mother also flew over the hump about 50 times. The 驼峰航线, very, very dangerous. So this is a bit of my family history in relation to the history of Wuhan. Now let's focus on carbon fiber multifunctionality. Continuous carbon fiber is very important for lightweight structures because of their high modulus, high strength, and low density. And they are widely used as a reinforcement in polymers. And carbon fiber reinforced polymer is abbreviated CFRP. And now CFRP is widely used in aircraft, for cars, for bicycles, for turbine blades, for robot arms, and for golf clubs, for tennis rackets, for fishing poles, and also for retrofitting concrete structures. The properties of carbon fiber include mechanical, electrical, thermal, and chemical properties. I'm going to focus on the electrical properties. Multifunctionality in structural materials means that the material serves structural and non-structural functions. An example of a non-structural function is self-sensing. No device involved because of, and therefore low cost and high durability and no mechanical property loss. Also, design simplification and large functional volume. So structural self-sensing means that a structural material senses itself without sensor incorporation. And the science of that is based on the structure property relationships, with the properties being the electrical properties. Self-sensing means that the structural material itself is the sensor. So if a load is applied, certain electrical property of the material changes. As a result, by using a meter, for example, one can sense what's going on. Damage of aircraft can occur, as shown here, due to bird strike. Okay? So it's important to be able to monitor the damage. And electrical monitoring is very feasible, as I'll show you. There are three kinds of electrical properties: resistance, capacitance, and inductance. Resistance is the most commonly used method, very long studied. There are these three material properties which pertain to the electrical behavior: the conductivity, permittivity, and inductance. And the conductivity is the most widely used material property for attaining the smart functions. Applications exploiting the electrical conductivity include lightning protection, de-icing and anti-icing by resistance heating, electromagnetic interference or EMI shielding, also battery electrodes and supercapacitor electrodes, also structural self-sensing by resistance measurement. Obviously, for this, the material must be conductive, and carbon fibers are conductive. The applicability of resistance-based self-sensing include this is applicable to carbon fiber composites without modification, but it's not applicable to glass fiber composites unless a conductive filler is present. For sensing matrix cracking, conductive filler incorporation helps. The disadvantages of material modification are that the increased material and processing cost, for instance, carbon nanotube or CNT added, is expensive, and also the CNT is difficult to disperse or be infiltrated. The applicability with material modification, the applicability is limited to new structures, not to existing structures which do not have the modification. Now, in making a carbon fiber polymer matrix composite, such as using epoxy resin as the matrix, then during the composite fabrication, the epoxy resin shrinks. As a result, it causes the carbon fibers to experience a compressive residual stress after the composite fabrication. Therefore, if after the fabrication you apply tension to the carbon fiber, you would cancel off that residual compressive stress, and that causes the resistance to go down. And this, we measure the resistance of a single carbon fiber with it being embedded in the middle here with epoxy that has been cured. And I have 4 electrical contacts labeled A, B, C, D to apply the 4-probe method to measure the resistance of this single carbon fiber. And as tension is applied, the residual compressive stress becomes canceled and the resistance goes down. So indeed, that's what we observe, and it's reversible. Thus, if we use not a single fiber now, but use continuous carbon fiber epoxy matrix composite and give it not just one cycle, but numerous cycles of tensile stress application, one finds that in every stress cycle, the resistance goes down, and it's reversible. Now, for a continuous carbon fiber laminate with an insulating matrix, such as epoxy, the through-thickness resistivity is never infinity, and that's because of fiber waviness, which causes a degree of fiber-fiber contact. So if upon elastic longitudinal tension, that is horizontal tension, the fiber waviness would decrease. So the degree of fiber-fiber contact along the through-thickness direction would be reduced, so the through-thickness resistivity would increase. Okay? Therefore, upon horizontal or longitudinal tension, we can monitor the through-thickness resistance, and we find that the through-thickness resistance increases every time one tensions, and that is because of the fiber waviness being decreased, and so the through-thickness resistance increasing, and it occurs reversibly. Now, damage of an aircraft can be due to bird strike and hail strike and so on. So damage monitoring is important. Composite material damage mechanisms include fiber fracture as well as interlaminar degradation. And both of these mechanisms cause increase in the resistance, and it's an irreversible increase. So we can use the resistance measurement to monitor fatigue. This is tension fatigue with the tension applied in the fiber direction and the resistance measured in the same direction. And we see that every time one tensions, the resistance goes down, as I explained before. And after so many cycles, we see the first increase in the baseline of the resistance, and that is because the first occurrence of fiber breakage. Note that the fiber breakage does not occur at every cycle, but in spurts. Okay? Now, a fiber toe means a fiber bundle, such as 12,000 fibers in a toe. And the composite involves fiber toes. Okay? And this is the second time of fiber breakage occurring at this high number of cycles. And each breakage involves only a fraction of a toe. And this is still later, still a larger cycle number. And here, this is the second fiber breakage. And still later, we see fiber breakage occurring at every cycle. So the baseline resistance climbs up incrementally in every cycle until it's close to breakage and the baseline resistance goes up a lot. Okay, so we can track by resistance measurement the complete fatigue life. And this shows the complete fatigue life, and the peak fractional change in resistance is shown. By peak, I mean it's down, up, and that up, that's what I call the peak. And we find that resistance has the first spurt of increase around 50% of the fatigue life, and it comes in spurts, and later on it's continuous, not in spurts. And along with this increase in the resistance is the secant modulus decreasing, thus confirming that indeed we have damage occurring. There are three types of resistance measurement methods: the volume resistivity for sensing a volume, the contact resistivity for sensing an interface, and the surface resistance for sensing a surface region. And all the resistance that I've talked about so far belongs to the volume resistance or the volume resistivity. But now I want to switch from volume resistivity to contact resistivity for sensing an interface. A composite laminate consists of a number of laminae or plies, And the interface between the plies is called the interlaminar interface. And this interface is the weak link. This is a microscope view of such an interface between two laminae, A and B. Okay, and the interface is a matrix-rich region, and that is the weak link. And if we can zoom in electrically at this weak link by measuring the contact resistance of this interface, one can monitor the condition very, very sensitively. Although the matrix is not conductive, the contact electrical resistivity is not infinity because of the fiber-fiber contact across that interlaminar interface. Delamination obviously decreases the interlaminar fiber touching, and so it increases the through thickness interlaminar resistivity. Okay, so the interlaminar interface resistivity is very sensitive to delamination or degradation of the interlaminar interface. I developed a modified four-probe method for measuring the contact resistivity of the interlaminar interface, or for the interface between two objects in general. These are the two objects in the two colors. I used two current contacts here and there, and two voltage contacts here and there. And these two objects have an interface, which is the square junction. And this method works very well, provided that the contact resistance is considerably larger than the volume resistance of the four legs that stick out. The contact resistivity is equal to the contact resistance of this junction times the contact area, that is the area of this junction. Now, this method is also valuable for allowing 2D spatially resolved sensing, because each overlap region is a sensor. So we have a sensor array in the form of a carbon fiber polymer matrix composite comprising, in this illustration, two cross-ply laminae. Now here is an aircraft that fell from the sky to New York City, killing over 200 people there. And it turned out that the tail got detached. And fastening is the issue, because the joining involves fastening. And fastening in general involves squeezing or compression. So it is important to monitor how well is this squeezing. Does it get loose or not? So one can measure the contact resistivity of the interlaminar interface during different cycles of squeezing at different stress amplitudes. And every time one squeezes, the contact resistivity decreases because of the increased proximity between the laminae, and so more fiber-fiber contact across the interlaminar interface. And note that this decrease of the contact resistivity of the interface is not totally reversible. And that's not good. That means there's irreversible change in the composite due to this squeezing. However, instead of using an epoxy matrix, one uses a thermoplastic matrix. Then we have total reversibility. Another nice thing about contact resistance measurement of the interlaminar interface is that one can have 2D spatially resolved sensing, because each overlap region is one sensor. So you have a 2D sensor array. And in this case, you have two cross-ply laminae. They don't have to be 90 degrees, but this is drawn 90 degrees. And anyway, you have 2D spatially resolved sensing achieved. This aircraft fell from the sky onto New York City, killing over 200 people. And that's because the tail came off. And the tail was attached to the rest of the aircraft by fastening. And fastening involves squeezing or compression. Okay? So it's important to look at the consequence of the squeezing, whether the fastening is still good or not. So we can measure the contact resistivities during the squeezing. So here is squeezing at different stress amplitudes, and we monitor the contact resistivity of the interlaminar interface, and we find that every time one squeezes, the contact resistivity goes down, and that is because the squeezing increases the proximity between the adjacent laminae, thus increasing the contact, the fiber-fiber contact across the interlaminar interface. And so this contact resistivity decreases upon squeezing. But it's not totally reversible. And that means that the microstructure of the interface is changed irreversibly a little bit every time you squeeze. However, if one replaces the epoxy matrix by a thermoplastic matrix, see, the contact resistivity decrease is totally reversible. And that is because the thermoplastic matrix is more tough than the epoxy matrix due to the linear chains in the thermoplastic and the cross-linked structure of the thermoset or epoxy. Okay. Now, upon elastic through-thickness compression, as I said, the through-thickness resistivity decreases, and that's due to enhanced through-thickness fiber proximity. But this effect also promotes the longitudinal, the horizontal direction, current path detour that's necessitated by fiber imperfection, which is always present. And that would cause the longitudinal resistivity to decrease. So instead of measuring the through-thickness resistivity decrease, one can measure the longitudinal resistance decrease. And both work to allow us to monitor the effect of through-thickness compression. Here is damage of aircraft nose by hail, and impact sensing is needed. And the contact resistivity of the interlaminar interface turns out to be very sensitive to impact. And this is that contact resistance during impact at progressively increasing impact energy. And every time one impacts, the contact resistance goes down irreversibly. Even at a tiny impact energy of 0.8 millijoules, we can still see that irreversible decrease in the contact resistivity of that interlaminar interface. And this decrease is because of the irreversible increase in the fiber-fiber contact across the interlaminar interface. The interlaminar interface can also be used as a temperature sensor, that is a thermistor, which refers to a temperature sensor based on resistance measurement. And this is the contact resistivity versus temperature, and it decreases upon heating. And that is because the chance of electrons jumping across that interface is enhanced by the heating, thus promoting the through-thickness conduction and therefore decreasing the contact resistivity upon heating. We can also monitor thermal damage as well as the temperature at the same time using this interface as the sensor. Shown at the bottom is the temperature variation, and up here is the variation in the contact resistivity of the interface. And every time one raises the temperature, the contact resistivity goes down, as I mentioned before. But note that at the highest temperature, the contact resistivity shoots up, shoots up like that. That's an indication of some very minor thermal damage. If we raise the highest temperature, then that shooting up becomes more prominent, and you have some aftermath there. Still higher temperature, then the shooting up becomes even more, and the aftermath becomes even more prominent. So the interlaminar interface is a very sensitive sensor for temperature as well as thermal damage. Now I move on to the third resistance measurement method, which is surface resistance for sensing a surface region. Surface resistance means you inject current from the same surface so that the current penetration is limited to a surface region. Okay? There's incomplete penetration of the current. Now, this is particularly valuable for sensing flexure or bending because one side is feeling horizontal compression, the other side is feeling horizontal tension. And one can apply 4 electrical contacts on each of the 2 opposite surfaces, one for measuring the top surface resistance, the other for measuring the bottom surface resistance. So during flexure, every time one flexes, the surface resistance on the compression side decreases, and that's reversible. And on the tension side, it's just the opposite. Every time one flexes, the surface resistance on the tension side increases. This has to do with the fact that upon flexure, the tension surface resistance increases due to the fiber waviness decreasing, and the consequent current penetration also decreasing. And when the current penetration decreases, then the surface resistance would increase. And for the compression side, it's just the opposite, because the compression surface would have the fiber waviness increase, and so more current penetration, and so lower surface resistance at the compression side. I invented smart concrete back in 1993. It contains a small amount of short carbon fiber. And this is the result of that cement with short carbon fiber under flexure, again using surface resistance measurement. And again, we see that on the tension side, the resistance, surface resistance increases every time one flexes, and the surface resistance on the compression side decreases every time one flexes. So these results for carbon fiber cement is consistent with what I said earlier for the carbon fiber reinforced polymer. And also, it is consistent with the effect of uniaxial tension or uniaxial compression on the volume resistance. That is, under uniaxial tension, the short carbon fiber cement increases. Under uniaxial compression, the volume resistance decreases. So the effect on the surface resistance under flexure are consistent with the effects of uniaxial tension or compression on the volume resistance. The volume resistance measurement would, if you use this instead of surface resistance measurement, you measure the volume resistance during flexure, like you use parametric as opposed to surface electrical contacts. The volume resistance would undesirably average out the opposite effects on the tension and compression sides. So that would not give you much sensitivity in monitoring the flexure. However, quite a number of papers published use this method. carbon nanotube, or CNT, has received a lot of attention. And I should mention, first of all, that the 4-probe method versus 2-probe method are very different. The 2-probe method includes the contact resistance of the two contacts in the measured resistance, whereas the 4-probe method essentially excludes the contact resistance from the measured resistance. And both the contact and specimen resistances may change upon stress or heat application. So if you use the 2-probe method, you have not just the specimen changing, you have the contact quality changing. So both things changing. So it's hard to find out what's going on. Piezoresistivity refers to the change of the electrical resistivity due to strain. And the gauge factor is defined as the fractional change in resistance per unit strain. And this is the carbon fiber cement under repeated uniaxial compression using various strain amplitudes shown by thin lines and the resistance shown by bold lines. And every time one compresses, the resistance decreases, as I mentioned before. And this is the 4-probe method. And we can plot the resistivity at the strain, the peak of the strain at each strain amplitude versus the strain amplitude, and connect the various data points chronologically. And one finds that it's more or less linear, not too much hysteresis, so that's good. This is obtained using the 4-probe method. But instead, if one uses the 2-probe method, it's terrible. And that's why the 2-probe method is really unreliable. However, a lot of published work has used the 2-probe method. The origin of the piezoresistivity in carbon fiber cement, for tension, the resistance increases. And that's because of fiber pullout, and thus causing the fiber cement interface loosening. Under compression, the resistance decreases because of fiber push-in and the consequent fiber cement interface tightening. This is the gauge factor for various conductive admixtures in cement as obtained by using the 4-probe method. I exclude the published results using the 2-probe method. So all these are based on the 4-probe method. CF means the short carbon fiber, and CNT is the carbon nanotube. And one sees that comparing CF versus CF plus CNT, you see that with the CNT added, the gauge factor actually decreased. See? On the other hand, if one has only the CF and no CNT, the gauge factor are all pretty high. Okay, and so the CNT here CNT alone is not so great in the gauge factor. So using the CF in the absence of CNT is most effective in giving the highest gauge factor. The reason why the CNT is not so helpful is the intertwined morphology. So, you know, it's not individual CNTs or nanofiber, and they're clumped together. And that's why they are not so effective. Now, freeze-thaw damage of concrete, that's a very serious problem because the water expands upon freezing, and inside the cement or the concrete, you have some free water. And so if you have multiple cycles of freezing and thawing, you would have degradation. And this this degradation process can be monitored very effectively by resistance measurement. Here in thin line is the temperature varying from below 0 C to plus above 0 C. And in thick line is the resistance or resistivity. Every time the temperature goes down, the resistance goes up. Okay. This is the volume resistance that's being measured. Okay. And this trend is like what I mentioned before. That is, when you decrease the temperature, there is less thermal energy for the electrons to overcome certain diffuse interfaces inside the cement. As a result, you would have higher resistivity. But interestingly, there is this incremental rise in both the upper envelope and the lower envelope of the resistivity as the freeze-thaw cycling progresses. That means the damage due to the freeze-thaw cycling occurs in every cycle until at the last cycle, it dies or fractures at the coldest point of the last cycle. Okay. And this is the first time that freeze-thaw damage is monitored in the entirety of the freeze-thaw life in real time. Traditionally, people don't do it in real time, but they evaluate by measuring the residual strength, how much strength is left after so many cycles of freeze-thaw cycling. And that's not very sensitive. Okay, as I mentioned, there are three types of material electrical properties: conductivity, permittivity, and inductance. I've spent a lot of time on conductivity. Now I move on to permittivity. Permittivity relates to the polarizability. And the polarization gives rise to an electric dipole, that is separation between the positive and negative charge centers. One can have polarization under DC. This is plus and minus, the DC applied voltage, and that causes the polarization. The plus sucks the minus. And so as you apply the DC voltage, the polarization builds up. And note that this polarization causes a voltage which opposes conduction. As a result, the apparent resistance goes up as the polarization builds up. However, if one suddenly reverses the polarity, so plus, minus, now reverse to minus, plus, the polarization cannot instantaneously revert in polarity, so it stays. So now the polarization aids conduction as opposed to hindering conduction. As a result, the apparent resistance goes down suddenly from R1 to R2. Okay? R1 is above the true resistance, R2 is below the true resistance. Okay? So one can have a means of looking at polarization through resistance measurement. And in this case, it's not the true resistance, but the apparent resistance. Okay. A number of applications that exploit the permittivity, all conduction-based applications, because the polarization hinders conduction. Also, the following applications. Capacitor is widely used in electronic circuits. And a capacitor involves polarization of the material between the two parallel plates in purple. And that results in charge magnitude Q at the two plates. And the capacitance is defined as Q divided by the voltage applied between the two plates. One can have structural capacitor for energy storage, say by using some conductive part of the structure composite as the electrode, and other parts that is non-conductive as the dielectric, being sandwiched by the two conductor sheets. The permittivity is also very important for battery and supercapacitor, particularly the electrolyte in these electrochemical devices. In addition, we can have structural self-sensing that's based on capacitance measurement as opposed to resistance measurement. The nice thing about capacitance measurement for structural self-sensing is that the material does not need to be conductive. So the applicability of capacitance-based self-sensing involves all polarizable materials, regardless of their resistivity. It's even applicable to conductors because the polarization of conductors occurs due to electron-atom interaction. Okay? And poling is not required. And depoling occurs spontaneously after poling because of the associated entropy increase. And poling is not feasible for large structures anyway. Piezopermittivity means the effect of strain or stress on the permittivity. Kappa, I call, is the relative permittivity. And the sensing effectiveness is the fractional change in capacitance per unit strain. And this sensing effectiveness is positive. Then we call it positive piezopermittivity. If the sensing effectiveness is negative, we call it negative piezopermittivity. This illustrates negative piezopermittivity in the transverse direction of cement when the compression is vertical. So horizontal is transverse, and the horizontal capacitance decreases. This is the fractional decrease in that horizontal or transverse capacitance due to the normal stress. So it's negative piezopermittivity in the transverse direction as shown, and not shown is the positive piezopermittivity in the longitudinal or vertical direction. The origins of capacitance-based damage sensing ability include these two: the effect of damage on the electric field lines between the two electrodes, and the effect of damage on the permittivity. Here shows the effect of damage on the permittivity, which can be obtained by plotting the measured capacitance versus the area being probed. And here we have two electrodes. Each has a number of segments, and we can have one segment, A versus A, or 2A versus 2A, or 3A versus 3A, or 4A versus 4A, okay, for the two segments, for the two electrode strips. And so this capacitance is versus NA, and the slope is proportional to the relative permittivity. Okay, and here we have the left part of the material, the cement, is perfect. The right part is defective, and the defective part has lower permittivity, which I call kappa, and so the slope is less for the defective region. So we can see the place where it changes slope, and that place corresponds to where the interface is between the good and bad regions. In 3D printed material, the sensing of stress or defect is very much needed. Sensor embedment in a layer of the printed material is not feasible. It's just too tiny. Okay. Cameras are widely used during printing, but they cannot see interlayer or subsurface defects. But we can use capacitance-based defect self-sensing in 3D printed polymer. We artificially positioned these dots, which are artificial damage that occur at certain layers below the top layer. Okay, and we control where these defects occur. Okay, and N is the number of layers above the defects. And we measure the capacitance using these two strips of electrical contacts. And as you have more defects, the capacitance goes down because the electric field is hampered by the presence of the defects. So the capacitance goes down the more defects you have. And this shows the capacitance versus the number of layers above the defects. And the more is the number of layers above the defects, the bigger is the capacitance because the defect is deeper down, and you are measuring the capacitance using coplanar electrodes that are on the top surface. Okay. Also, the larger is the number of defects. You have shown the picture of 7 defects, but I can have 0, 1, 3, 5, 7, different numbers of dots there. And the larger is the number of defects or dots, the lower is the capacitance. Okay. Here's continuous carbon fiber polymer matrix composite with tension in the fiber direction. And up here is the relative permittivity, which I call kappa, during a tension application, 3 cycles of loading at progressively increasing stress amplitude. And you can see that the relative permittivity increases quite reversibly every time one applies tension. And that is a positive piezo permittivity. At the same time, we can measure the resistivity. The resistivity also increases reversibly every time one tensions, and that is positive piezo resistivity. In general, the resistivity and permittivity are related through Kramer's chronic relationship. Pyropermittivity means the effect of temperature on the permittivity. And shown here is polycrystalline graphite, and the relative permittivity increases quite reversibly upon heating. It's just heating to 70 degrees C. So one can use the permittivity to sense the temperature. And also it can be used for energy conversion, converting thermal energy to electrical energy. The origin of pyropermittivity, the effect of temperature on the strength and abundance of the carrier-atom interaction. Carrier meaning the mobile charges like electrons. Also, the origin relates to the effect of temperature on the carrier concentration and mobility. Now, here again is a fiber tow, such as 12,000 fibers in a tow. The fibers in a tow are resistors in parallel, as indicated by the fact that the resistivity is the same for a single fiber and a tow. Now, poling is not needed. And all I talk about doesn't involve poling. The relative permittivity we measure for a single carbon fiber is 8 times 10 to the 7. For a tow with 12,000 fibers is 1.2 times 10 to the 4. 4 orders higher for the single fiber than the tow. And that's because the tow amounts to 12,000 resistors in parallel, and hence the resistance is 4 orders higher for the single fiber than the tow. A high resistance promotes polarization, and therefore the permittivity becomes higher. Now, if the tow were 12,000 capacitors in parallel, the tow permittivity would have been only 7 times 10 to the 3, less than the measured value of 1.2 times 10 to the 4. That means the tow is not exactly 12,000 capacitors in parallel due to the fiber-fiber contacts in the toe. And this is what I mean by fiber-fiber contact, resulting from the fiber waviness. This is the transverse direction. The permittivity, as high as 10 to the 8th, as I mentioned, is higher than that of non-conductors, like ceramics or polymers, by orders of magnitude. And that is due to the low electric field needed to cause the carriers, that is electrons, to move in a conductor. And this colossal permittivity actually is as predicted theoretically for conductors in general by Johnshire back in 1999. Now, conventional polarizable materials are insulators, ceramics and polymers. But here I'm talking about conductors, and the conductors exhibit colossal permittivity. Upon rolling, the microstructure is refined. Okay. So carbon cannot be rolled, it's too brittle for that, but metals can be rolled. So we took copper and steel sheets and rolled them, and we find that the rolling causes the permittivity to increase quite a bit. This means that the permittivity is enhanced by the microstructural refinement. Okay. Now, for a conductor, if the electrons just move around without interacting with the atoms in the conductor, then there's no polarization. But if the electrons, at least a fraction of the electrons, interact with the atoms in the conductor, then there would be polarization. Okay? So polarization in conductor requires a degree of electron-atom interaction. And it turns out that it's just a very small fraction of the mobile electrons interacting with the atoms. And the interaction is mainly occurring at microstructural heterogeneities, such as the grain boundaries. Thus, rolling increases the permittivity. Polarization involves engagement of the carrier-atom interaction, whereas depolarization under reverse polarity involves disengagement of this interaction. This shows the relative permittivity versus grain size for polycrystalline graphite. The smaller is the grain size, the higher is the permittivity. And if one plots versus 1/, grain size is more or less linear, that means the carrier-atom interaction occurs mainly at the grain boundaries. Due to the inherent polarization, there is inherent AC capacitance. Okay, that you don't have to pole it. That's what I mean by inherent. No poling needed. There is capacitance there. Okay, and if one short circuits the thing, then the capacitance would go down. That's capacitance discharge. And subsequently, if you open circuit it, it would charge back. This is self-charge. That's kind of a new thing, self-charge. And I showed you this before, and this is a case of polarization, depolarization, symmetry. You see the curve R1, R2 is symmetry. We call it polarization, depolarization, symmetry. Okay. However, in reality, it's not symmetrical. This is for polycrystalline graphite and at different currents. The higher the current, the higher is the polarization. Okay, so the higher is the apparent resistivity, and the greater is this asymmetry, what I call polarization, depolarization, asymmetry. Okay. And here is uncoated carbon fiber in thin line and nickel-coated carbon fiber in thick line, and you can see it's asymmetrical. Okay? Polarization, depolarization, asymmetry. However, if you depolarized by short circuiting for like 6 minutes right before the electrical testing, it is symmetrical, okay, for both nickel-coated and uncoated carbon fiber. Okay. Now notice the nickel-coated carbon fiber has higher polarization than the uncoated carbon fiber. And that's because the nickel coating enhances the polarization due to the increased carrier concentration. Nickel is a metal. And the polarization, depolarization asymmetry is due to the difference in the rate of carrier atom interaction engagement, polarization, and the rate of carrier atom interaction disengagement, that is depolarization. So naturally it's asymmetric, but we can kill the asymmetry and force it to be symmetry by short circuiting immediately before the electrical testing. I mentioned about rolling, and this is copper, it is 0% cold work, that is no rolling, 37 cold work, that's after rolling, and more rolling, that is more cold work, there's higher polarization and also more polarization, depolarization, asymmetry. And after subsequent annealing, it becomes very small polarization, also symmetry. So cold work enhances the polarization, depolarization, asymmetry, whereas annealing reduces it. Hence, the microstructure affects the behavior. Now I move on to yet another aspect of permittivity behavior, and that is electret, which refers to the permanent electric dipole. Conventional electrets are insulators, ceramics and polymers. There is inherent electret. Okay? That means DC voltage can be provided, as inherently provided. Okay? You don't have to pole it. It's already there. And the voltage obviously has to change sign upon polarity reversal. And this voltage would diminish to 0 upon short circuiting. That's discharge. And then afterward, if you open circuit it, it charges back. That's self-charge. And this is for the case of carbon fiber tow, uncoated, and 3 cycles of discharge charge. So it's very reproducible from cycle to cycle. You have short-circuited discharge and afterward open-circuited self-charge. And this electric field associated with the electret increases with decreasing grain size, again indicating that the electret involves polarization with the carrier atom interaction responsible for the polarization occurring at grain boundaries. Again, we can look at the inherent electric field for copper after different degrees of cold work or cold rolling. The more is the amount of prior cold work, the greater is that inherent electric field of the electret, and also the greater is the degree of asymmetry in that polarization, depolarization, asymmetry. Okay. So this again points to the importance of the microstructure refinement in giving the promoting the polarization, and cold work would give you more microstructural refinement. That's more electric field and also more polarization, depolarization, asymmetry. Even more important is the fact that the positive end of the voltage in the electret is where the rolling starts. This means that the electrons move with the atoms during rolling. And this is in line with the occurrence of electron-atom interaction. The mechanisms of electret formation are twofold, electrical and mechanical. The electrical involves polarization, depolarization, asymmetry. the mechanical involves directional deformation. Now, conventional capacitance are all based on the permittivity, as I explained before. The capacitor discharge or charge occurs like this in an exponential way. The charge decreases exponentially during discharge and increases exponentially during charge. However, in the case of the electrodes, I introduce a new scientific quantity, which I call electrode-based capacitance. The conventional is the permittivity-based capacitance, C, which is defined as Q over V, with V, the voltage, driving Q, the charge, on each plate. But the electrode-based capacitance, I define as C prime, which is Q prime divided by V prime. Q prime is the electric charge, which is determined by discharge testing. This current versus time during discharge, the area under the curve gives you the charge Q prime. And V prime is the electric voltage. And Q prime drives V prime. The C prime, the electrode-based capacitance, is higher than C, the permittivity-based capacitance, by 9 orders. For single carbon fiber, C prime is 10 to the 4 farad, and C is 10 to the minus 13 farad. Okay? So huge electrode-based capacitance. The electrode-based capacitance discharge involves a discharge time constant, which is equal to RC prime, and discharge energy equal to half C prime V prime square. Conventional capacitors would be RC and CV, half CV square, right? But now instead of C is C prime, instead of V is V prime. C prime is the electrode-based capacitance, V prime is the electric voltage. And this has been experimentally shown for a variety of metals and carbons. So the electric discharge charge boils down to the electrode-based capacitance discharge or charge. The applications of electrodes, electrode filter, and that is utilized for the COVID mask already. Okay. The electrode, because it's charged, it can attract certain particles. Also, buildings for cleaning the environment using electrode facade rather than plants for attracting certain particles. Also, battery electrodes and supercapacitor electrodes having an electrode voltage may be advantageously used to promote the performance of the battery or supercapacitor. Also, low power source. The power provided by the electrodes is very, very small. We're talking about low voltage and low current, but low power source has its industrial need. So this is a summary of the permittivity behavior. Colossal permittivity. The capacitor or electric discharge upon short circuiting, and it charges back upon subsequent open circuiting. That's self-charge. Polarization is inherent. Poling is not needed. Inherent polarization, depolarization, asymmetry can be removed by short circuiting. Directional mechanical deformation strengthens the electric behavior. The tailoring of the permittivity behavior of conductive materials is an emerging field of science. Also, emerging is the field of structural permittivity, that is, structures providing permittivity-based functions. Now I move on to the third type of electrical properties of materials, and that is the inductance. Conventional inductors are in the form of metal coils. And the inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. So in red is the primary current, in green is the opposing induced current. Inductors are used in electronic circuits, Also in power transformers for transferring electrical energy from one electrical circuit to another. Also, they are used in electric generators, which converts mechanical energy to electrical energy. Also, inductors are used for electric motors, which convert electrical energy to mechanical energy. Almost 100% of electrical energy in the world is produced by generators, and motors consume about 65% of electricity. Magnetic energy storage also involves inductors. But here, I'm not talking about inductor coils. I'm talking about uncoiled material as inductor. This is an emerging field without coiling, so it's compact. And that enables structural inductor, that is new structure providing the inductor function. This is a new functionality of structures. Also, it allows structural self-sensing by inductance measurement. And for that, the material needs to be conductive. So uncoiled carbon fiber, we discovered to be an inductor. And that inductor function stems from the microstructure of the carbon fiber. You can see these carbon layers inside a single carbon fiber. They're crooked, okay? It's not coiling, but it's a bit like coiling, okay? And this is another rendition of the microstructure, showing interlinking of the carbon layers within a carbon fiber. So because of this microstructure, the coilless single carbon fiber as inductor provides 2.4 millihenry per meter of inductance. And this is higher than the value calculated based on the dimensions by a factor of 1100. So this high permittivity is almost all due to the microstructure. Now let's move from single fiber to tow. Okay, 12,000 fibers in a tow. Okay, the measured single fiber inductance per unit length is 2.4 millihenry per meter, compared to only 1.7 microhenry per meter for the tow volume. Again, the calculated inductance is based on the dimensions. And the ratio of the measured to calculated inductance is less than 1 for the tow, but it's up to 1100 for a single fiber. Thus, the microstructure of a single fiber contributes to the inductance much more than the fiber-fiber contacts in a tow. The fiber waviness causes fiber-fiber contacts in a tow, and thus contribute to the inductance. Okay. The question is, are the fibers in a tow inductors in parallel? The tow volumetric inductance, measured using two parametric electrodes, is 1.5 microhenry per meter, and that's much less than the single fiber value of 2.4 millihenry per meter, as I already mentioned. Now consider that a tow consists of 12,000 inductors in parallel. Then the apparent single fiber volumetric inductance would be the tow volumetric inductance times 12,000, and that becomes 18 millihenry per meter. But this 18 millihenry per meter is higher than the measured value of 2.4 millihenry per meter for the single fiber. Thus, the model of inductance in parallel is not exactly obeyed. The fiber-fiber contacts in a tow contributes to raising the tow inductance by 87%. Now I introduce a new concept. It's a new scientific quantity, which we call surface inductance. This is obtained by having surface current as injected by using surface electrodes. So we have partial current penetration. That's in contrast to the volumetric inductance, where you have complete current penetration. Let's consider carbon fiber tow, comparing volumetric inductance versus surface inductance. The volumetric inductance of the tow as I already said, it's very little, 1.7 microhenry per meter, much less than the single fiber measured value of 2.4 millihenry per meter. But the tow surface inductance, measured using two surface electrodes, is 4.2 millihenry per meter, is about equal to the single fiber volumetric inductance of 2.4 millihenry per meter. The ratio of the volumetric inductance to the surface inductance of the tow is 1.7 microhenry per meter divided by 4.2 millihenry per meter. That's 4 times 10 to the minus 4. So the fraction of the tow contributing to the surface inductance is this value, this times this fraction of the tow. Okay, so this times 12,000, that means 4.9 fibers only. Only a fraction of each fiber at the surface is probed. The apparent single fiber inductance is 4.2 millihenry per meter times 4.9. Okay, and that equals 21 based on the surface tow inductance. But based on the volumetric tow inductance in the previous slide, it's 18. And so these are pretty close, 21 and 18. So things are consistent. Okay. The volumetric inductance and surface inductance results are consistent with one another. And the surface inductance is huge compared to the volumetric inductance. Twisting the tow enhances the handleability of the tow and is widely used, especially for weaving. And we discovered, and the twist level, how much twisting, we can tell by inductance measurement. This method of twist level self-sensing by inductance measurement is fast, low cost, and large format. No scanning required. The long tow, you can measure the inductance, and from that tell the twist level. And this shows the fractional change in resistivity, and it decreases as you have more twists because the number of fiber contact points is increased by twisting, so the resistivity decreases. However, the inductance increases, and the fractional increase in the inductance is high compared to the fractional decrease in the resistivity. And so the inductance increases with the number of twists of the tow, and that provides the inductance-based self-sensing of the twist level of carbon fiber tow. Tension on the tow also affects the inductance, and this is called piezo inductance, and this shows the effect of cyclic tension. Okay, here, 5 cycles at progressively increasing stress amplitude, and the inductance increases every time you stress it, and the effect becomes bigger and bigger as you have more and more twists. Okay, so the piezoinductance is not totally reversible, but is enhanced by twisting. Now I move from tow to CFRP, which is carbon fiber reinforced polymer. This is a two cross-ply laminate, and you can see that if you go in this 45 degrees direction, the current path has to change direction. This is current path tortuosity. That's not coiling, but it's a bit like coiling. Okay, and that should increase the inductance. The toe bending and toe-toe interface should also increase the inductance. Okay. The sources of inductance in continuous fiber composites include these: directional changes of the current path, that is the tortuosity of the current path, the fiber-fiber contacts in a toe, the toe bending, as illustrated here, the toe bending, promoting fiber-fiber contacts in the toe, also the toe-toe interface and the interlaminar interface. As a result, the inductance is much higher for CFRP than the toe. And this is what I mean by the toe-toe interface. And here is the interlaminar interface between the two laminae. The fiber-fiber contact across both toe-toe interface and interlaminar interface promote conduction path tortuosity. So this is woven carbon fiber reinforced polymer, just one lamina, and we compare the inductance in the 0-degree direction and the 45-degree direction. The measured inductance decreases with increasing width, whether 0-degree or 45-degree direction. And that is because of inductors in parallel. And here is the calculated inductance based on the dimensions. And note that the calculated value is very small compared to the measured value. And that indicates that the inductance is mostly like 87% due to the composite structure. The measured capacitance is higher for 45 degrees than 0-degree because of the conduction path tortuosity and toe-toe interface for the 45-degree case. And note that the calculated inductance is similar in the two directions because the calculated inductance is just based on the dimensions. And shown here is the length effect. The previous slide was the width effect. Now it's the length effect. The longer the length, the larger is the measured inductance because of inductors in series. And 45 degrees give higher inductance than 0-degree. And because of that, long, narrow composite components are suitable for providing high inductance. Now let's compare volumetric and surface inductance, as well as volumetric and surface resistance, and volumetric and surface Q. The Q refers to the Q factor. The surface inductance is huge compared to the volumetric, and the resistance is much higher, as expected, because of the small current penetration, and the Q is higher, okay, for surface Q than volumetric Q. And it's significant that, shown in red, the surface inductance reaches 14 Henry per meter, very high value. But we need to enhance the Q. To do that, we need to decrease the resistance. And one way to do that is position aluminum foil below or above the CFRP and measure the inductance of the CFRP aluminum combination. And the aluminum foil greatly increases the Q, and that's due to the decrease in the resistance in spite of the decrease in inductance. Now, composite laminates, that's in practice very important. What I showed you is just one lamina, okay? But in practice, it's not one lamina, many laminae making a laminate. So let's look at the effect of the number of laminae in the laminate, how that affects the inductance. The more is the number of laminae, the larger is the inductance. Okay. Now, if the laminae are inductors in parallel, the inductance should decrease as 1 over n, where n is the number of laminae. This means that the laminae are not inductors in parallel. Now, we have the inductance increases with n, but if it were inductance in parallel, it should decrease with increasing n. It's the opposite. And so this means that the laminae are not inductors in parallel at all. And this is due to the fiber-fiber contacts across the interlaminar interface, so that the interlaminar interface contributes to causing the inductance increase. Okay. So the more is the number of interlaminar interfaces, the higher is the inductance. And shown here is the ratio of the measured to calculated inductance, and it also increases with increasing laminae, increasing number of laminae. And this ratio, note that it gets very high, 1820, gets pretty high. And this large value means that the inductance is essentially not due to the dimensions, but is due to the material structure. And the similarity of this ratio for the 0 and 45-degree cases indicates that the total interface is not the main aspect of the material structure that contributes to the inductance and this ratio. Rather, it's the interlaminar interface that's the main aspect of the material structure that contributes to the inductance and this ratio. Note that the 0 degree does not involve total interface, whereas the 45 degrees involve the total interface. Yet, they have similarity in the ratio. Okay? And this is why I said that the interlaminar interface is the main aspect of the material structure that contributes to the inductance and the ratio. And this is the fractional change in inductance relative to the case of 2 laminae. And you can see that this fractional increase when you go from 2 laminae to 7 laminae, that is 3.5 times, gives you 3.5 times the change in inductance. So the two kind of jive. Okay. The resistance, on the other hand, decreases with the increasing number of laminae. That's expected. But this decrease in the resistance with the increasing number of laminae may contribute to the increase in inductance. Okay. The resistance and inductance are not independent of one another. There are other methods to increase the toe inductance: twisting, tensile loading, that is piezoinductance, and also using nickel-coated carbon fiber. So this is a summary of the inductance behavior. Single carbon fiber exhibits volumetric inductance that is 1,100 times that of the dimension-based calculated value, and that's due to the microstructure. The volumetric inductance of a toe is much below that of a single fiber. The fiber-fiber contacts in a toe contribute to raising the toe inductance by 87%. The surface inductance, a new scientific quantity, is huge compared to the volumetric inductance. The surface inductance of a toe is comparable to the volumetric inductance of a single fiber. And the surface inductance of a 1 laminar CFRP reaches 14 Henry per meter. The Q factor can be increased by positioning aluminum foil above or below the CFRP due to the resistance decrease in spite of the inductance decrease. The inductance, resistivity, and permittivity are higher for 45 degrees than 0 degree. And these they are not independent of one another. Okay. The volumetric inductance of CFRP increases with the number of laminae, and the inductance decreases with increasing width and increases with increasing length. The tailoring of the inductance and Q factor of a coilless material is an emerging field of science. So structural inductance and structural permittivity are provided by carbon fiber. These are new functionalities for structures. And this work provides the initial science base for this emerging field. I'd like to dedicate this lecture to the memory of Professor Millie Dresselhaus, my former mentor and PhD thesis advisor. I took her solid-state physics course at MIT and fell in love with the beauty of the physics. Her parents came from Poland and moved to the United States. She was born in the United States, and this in New York City, and with her mother here. And the family was pretty poor. They lived in the most dangerous part of New York City. But she became a prominent scientist, receiving the top honors in the world in science. And this is her receiving the Kavli Prize in Nanoscience in 2012, and also the National Medal of Science from President Bush, and the Presidential Medal of Freedom from President Obama. She loved science. Aha, that's her favorite word. And she instilled in me the love of science and the love of thinking out of the box and wanting to be a leader, not just a follower, and also the love of helping others succeed. And so I find joy in inspiring others. And I speak not only in universities, but in schools like this one in Hong Kong. IQ, intelligence quotient. EQ is emotional quotient, meaning the ability to go ahead in spite of difficulties. SQ, spiritual quotient, means understanding what you're living for, what's the meaning of life. And we need all three Qs to have a greater chance of success. And I want to thank Professor Dresselhaus, and I appreciate your allowing me to remember her. Thank you.